Hello class, this is section 2.5 and in this video we are going to talk about well-posedness, which is a very important property of partial differential equation. We say that a PDE is well-posed if small changes in the boundary only change the solution slightly. Let's use the Laplace equation to talk about why this might be important. So the Laplace equation is used to figure out steady-state temperatures of some surface given a boundary temperature. So let's say that we're trying to figure out what the steady-state temperature of a surface should be, and we do that by first measuring the temperature of the boundary. But let's say that I make a mistake, I make a small error, and I'm off in the temperature by 0.0001 degrees Celsius. Well, if that mistake of 0.00001 degrees Celsius completely messes up my calculation for the solution, I'm not going to be able to get an accurate steady-state temperature very often, am I? Because measurement tends to be imperfect. So this is very important if we want to use any of our PDEs in real life, that they be well posed. So if the Laplace equation is well posed, I could mess up the boundary temperature by 0.0001 Celsius, but that will result in the steady-state temperature only being off by 0.0001 Celsius, and that's perfectly acceptable. So let us consider two different boundary temperatures. The boundary temperature G corresponds to a steady-state temperature Vxy, and the boundary temperature F corresponds to a steady-state temperature U. We parameterize the boundary by theta and the interior of the surface by x and y. So let's assume that G and F are pretty close together, that the boundary temperatures are really close together, that G is just a slight perturbation of F. And technically we can say that the absolute value of G minus F is less than epsilon for some small epsilon and all theta on the boundary. Our goal is to show that U and V are also very close together. In other words, to show that the absolute value of Uxy minus Vxy is small in magnitude for every x and y on the surface. So just to clarify, the argument of f here is theta and not 0. Sorry for the bad handwriting there. So we want to show that Uxy minus Vxy is small, and we can define as we say that W is a function that's equal to Uxy minus Vxy. And our goal can be rephrased in this way: show that the absolute value of Wxy is small for all x and all y in the surface. So let's think about what the boundary conditions for W are. So if the boundary conditions of U is F and the boundary condition of V is G, it makes sense that the boundary condition of W is F minus G. And notice that since U is a solution of the Laplace equation and V is a solution of the Laplace equation, and that the Laplace operator is a linear operator, and therefore the Laplace equation is a homogeneous equation, this implies that W is also a solution of the Laplace equation. So we have Laplace of Wxy equals 0. So here we have a solution of the Laplace equation that has f theta minus g theta on the boundary. But we also know that f theta minus g theta lies between epsilon and minus epsilon. The difference between f and g is small. However, by the maximum principle, we know that the maximum and minimum of W must also be found on the boundary. But this means that W must also lie between epsilon and minus epsilon, because otherwise you would have a maximum or a minimum in the interior of your surface over here. But this is the same as saying that W is small for every xy, and it's the same thing as saying that u xy minus v xy, let's make this a more clearer, u is small, less than epsilon. And we are done. This implies that if g and f are very close together, that necessarily u and v are also very close together, and thus the Laplace equation is well posed.